Hello everyone and welcome to the channel. Now today in this video I'm going to solve all the questions which I have uploaded in the last week on Monday MCQ, right? The video got delayed because of all the hassle and bustle of the current scenario. But yeah, with this particular week I'll try to be regular on it. Right. So the questions were on organometallic compounds and many of you have solved it. A lot of you have sent your answers. So let's try to see and let's try to check that which are correct and how to solve these questions. Okay, so I'll be explaining in a very brief way the answers of these questions. So for the first question over here, it says that the correct order of thermal stability of the given compound is. Now in order to find out the number of, like, the thermal stability of a given compound, you need to look for the beta hydrogens. Okay, because there is a phenomena called as beta hydride elimination, which is shown in the metal alkyl, like metal alkyls basically. And if a metal alkyl or if a organometallic compound shows beta hydride elimination, in that particular case it is less thermally stable. Okay, so it should not have beta hydrogen. That is one of the case which should be there, right? Now here in this you can see that you have three types of complexes. You have titanium methyl, that means titanium with CH3. You have titanium ethyl, that means CH2 and CH3 is here, and the next one is like titanium, and with that you have CH2, and with C you have CH3, CH3 and CH3, right? So this is the third one, if you can see over here. Now if I mark the beta carbons over here, so it has, this is alpha, this is beta, here this is alpha, this is beta, here you don't have any beta, it's only alpha present, right? So that means what you can easily see that this particular group does not have any beta hydrogen. It has 3 beta hydrogen, so it will be least thermally stable. So this titanium and this ethyl part should be the least one in the list. So if you look on the options, your option A and option D seems to be the probable answer, because there only your titanium ethyl 4 is in the least position, right? Now looking upon the other two, how you have to manage or how you have to understand the other two, the first and the last one, is based upon one more phenomena which is called as alpha hydrogen abstraction. Okay, there is a alpha hydrogen abstraction which you will see. Now if you look for alpha hydrogen, because beta hydrogen both of them don't have. Okay, so now the next thing is you have to look for alpha hydrogen abstraction. So is there possibility of alpha hydrogen abstraction? So in this molecule, in this moiety, if you look, so there are two alpha hydrogens, so the alpha hydrogen abstraction can happen twice, whereas here you have 3 alpha hydrogen, so it can do 3 times more alpha hydrogen abstraction. So if I talk about the stability, so this one will be least stable, then this will be quite more stable than that, and the most stable one is goes to this, because it has 0 beta hydrogen and less number of alpha hydrogen. So the correct answer comes out to be your option number D. Alright, so option D was the correct answer for this. Alright, talking about the next question over here, it says that the efficient catalyst of hydrogenation of alkenes is RHPPH3 whole thrice Cl. However, iridium PPH3 whole thrice Cl does not catalyze this reaction, because now why this happens, I need to show you the reaction mechanism, and then only you'll be able to understand that what actually happens over here, right? So let's quickly understand that. Alright, so as the question deals with the hydrogenation of alkene by RHPPH3 whole tricycle, that is basically your Wilkinson catalyst. So, however, this particular iridium complex does not catalyze the reaction, because okay, there are 4 different options. PPH3 binds stronger to iridium than to rhodium. Chloride binds stronger to iridium than to rhodium. PPH3 binds stronger to rhodium than iridium, and the last one says that chloride bonds stronger to rhodium than to iridium. Now, if you look upon the mechanism, this is the mechanism of your hydrogenation of alkene by your Wilkinson catalyst. So, if you look that this is a square planar complex. Basically, in the first step, there is a loss of PPH3 ligand, making this particular complex trigonal planar kind of. And in the next step, hydrogen get, like, there is a cis addition of hydrogen, making the complex trigonal bipyramidal structure. And in the next step, your alkene comes and binds to this, making it octahedral moiety. In the next step, the hydrogenation happens, and then the like reductive elimination happens in the last step. So the first step, or the first step to activate this reaction or to activate the complex, is removal of PPH3. That means PPH3 has to remove. Now with rhodium, this PPH3 can easily get removed. With iridium it does not happen. That's why it is not useful for the catalysis, right? So there is no use of, like, chlorine does not have any role to play over here. Chlorine stays to the complex from starting to the end, so there is no option, no option can be correct which is related to chlorine. The only option which is correct is that pph3 binds stronger to iridium than to rhodium. That's why it does not breaks in the iridium complex, whereas in the rhodium complex it breaks, right? So this is going to be the correct answer for this particular question. All right, so talking about the next one, it says that electrophile pH3C plus reacts with this particular complex to give a compound A. The product A is formed because. So why product A is formed? So let's try to understand that. So over here, if you look this particular complex, what kind of species it is? Eta 5 will give you 5 electrons from here. Iron over here, from the in the neutral atom method, it's going to give you 8 electrons, right? And since you have CO, so each CO gives you 2 electrons, so 4 electrons from CO ligands, and this being a methyl kind of like methyl derivative, so it is going to give you 1 electron, and you have to remove one because of the positive charge. So overall if you find out, so it's a 8 plus 4 is 12 plus 5 is 17, so it's a 17 electron species. It's not a stable species, it's not 18 electron species basically. So what is going to happen basically? So first of all, this particular alkane is going to get converted into alkene kind of group, okay? Because it has beta hydrogen, so beta hydride elimination is going to happen in compound A, and that in that particular way it is going to get converted into alkene, and then it is going to react with this electrophile, okay? So electrophilic reaction or anything is going to happen only when your initial compound becomes 18 electron species, and that it can easily do by getting converted into 18 electron species. Now it's a 18, like it can become 18 electron species, right? Because right now it is like CDMe3, right? So it's like CD, and you have like CH3, and it's CH3, and it's attached to your iron, right? So it has, this is alpha and this is beta, you have beta hydrogen, so this will get eliminated and you will get carbon carbon double bond over here, right? So alkyl group will get converted into alkene over here. So option D is going to be the correct option for that. Alright, let's talk about the next one. It says that the correct statement regarding terminal bridging CO groups in the solid CO4, CO12 and IR4, CO12. For this particular question, you need to understand the structure of both of them. So I'll just show you that how these structures look like. Alright, so that's how it looks like. You can see this is CO4, CO12, the cobalt complex. So these are the 4 cobalts over here, 1, 2, 3 and 4. Now if I talk about the terminal carbonyls, so you have 1, 2, 3, 4, 5, 6, 7, 8 and 9. Yeah, so you have 9 terminal carbonyls, right? So the number of terminal carbonyls for your CO4, CO12 is 8. It's a wrong statement. It should have 9 terminal ones. Now how many bridging ones are here? So the number of bridging carbonyls over here, you can see this is 1, this is 2 and this is 3. So there are 3 bridging ones. So the number of bridging carbonyls is 4. That is also wrong, right? So the next one, which says that both of them have equal number of bridging carbonyls, that is also wrong, because in the iridium complex you can see there is no bridging carbonyl present over here. The difference is just because of the difference in the size, okay? Cobalt is a smaller molecule, whereas iridium is a bigger molecule. Number of metal-metal bonds and other things are same. It's just because that the size is different. That's why the bridging carbonyls are not here in the iridium complex. So in the iridium complex, you only have 0 bridging carbonyls, right? So the number of bridging carbonyls in the iridium complex is 0. That is true. So this is the correct answer, and you can only answer this if you know the structure. Okay, so that's why it's very important that you should know the structures as well. Let's get to the next question. Alright, so let's talk about this question now. It says that the stretching frequency of nitrosyl NO in the 16 electron complex having the following empirical formula. The empirical formula is iridium NOCl PPH3 whole twice CO plus is expected to be. So over here we don't know what kind of nitrosyl is it. Is it a linear nitrosyl or a bent nitrosyl, right? So first of all we need to find that out. So let's try to find out that how much electron does this nitrosyl is going to donate over here. So iridium is going to give you 9 electron. Let's say X electrons are given by this nitrosyl. Chloride will give you 1 electron. PPH3 is going to give you 2 electrons. So 2 times of PPH3 means 4 electrons from there. This CO ligand is again going to give you 2 electrons. One positive charge will reduce 1 electron, and overall it's a 16 electron species given in the question. So I'll put 16. When I will solve this, I will get, I think, when I will solve each and everything, 9 plus 1 is 10, plus 4 14, and plus 1 is 15, right? So overall I'll get 15 plus x is equals to 16. So my x value comes out to be 1. So it should be 1 electron donor, and we know that nitrosyl in linear form, like when it is in the linear form, it gives you 3 electrons, whereas in the bent form it gives you 1 electron. So this is bent nitrosyl. Okay, so once you got it as a bent nitrosyl, you should know the stretching frequency of that. So bent nitrosyl gives you stretching frequency around 1650 to 1500 centimeter inverse, whereas linear nitrosyl gives you at 1950 or higher than that. Okay, so since it's a bent nitrosyl, so the answer is 1650 centimeter inverse. All right, so this is how it has to be answered. All right, so the next one, it says that shock carbines are, okay, so what these shock carbines will be. So it's a property of your shock carbines, you all know. It's just a direct question from there, right? So shock carbines are triplet in nature, right? And they are nucleophilic in nature. So option A is correct. Okay. You just need to remember this, that Fischer carbine are singlet in nature and they are electrophilic in nature. Okay. FSE. Just remember that. Fischer carbine, singlet, and they are electrophilic in nature. So your shock carbine will be triplet and nucleophilic in nature. Okay. So you can remember in that particular way. So answer A is your correct option. Alright, so taking the next question over here, it says that the reaction this, you can see over here, the reaction this is an example of what kind of reaction is it. It's a very simple and a very straightforward question. I'll just draw the reaction mechanism. So you have manganese over here. You have 5 CO ligands. So let me just make those 5 CO ligands. Okay, and you have methyl group. Okay, this methyl group, and you are treating it with CO. So basically it's already it's coordinatively saturated molecule, so it will not undergo reaction unless and until there is a one migratory insertion which will happen in this. So after one migratory insertion, you will get something like this Mn, and you will get COCH3 that will be formed, and then you will be having, let's say, one empty space, and the other one CO will remain as it is. So at this empty space, this particular CO is going to come and bind. Okay, so the final product will be CO5 Mn COMe3. Okay, so this is COMe3. So what kind of reaction it is? This is migratory insertion. So option D is the correct option for this. Alright, let's talk about the next one. So it says that the decarbonylation reaction of cis, this is the molecule given to you. You are doing decarbonylation reaction and it yields X, Y, and Z three products. So the molar ratio they are asking. I'll just explain you in the next tab. So in this particular question, if you can see, it says that the decarbonylation reaction of cis, this particular complex CH3COMn 13COO4 yields X, Y, and Z three other molecules, where X is this, Y is also given to you, and Z is also given to you. Y is cis product and Z is trans product. The molar ratio of the product of X, Y, and Z are. Okay, so it's pretty simple. I have just drawn the molecule, basically the one which is given to you, and after reaction it is giving you X, Y, and Z. So you just have to see that in how many ways you can form X, Y, and Z. So if you talk about X, so what is happening, how X would have been formed, it would have just formed if this labeled carbonyl has been it has evolved as carbon monoxide, and this methyl group has came to this place as the reverse of 1,1 migratory insertion, and that's how it has been formed. Okay, quite similar to that. If you talk about Y, so in how many ways you can form this cis product basically. So this is one of the product which I have shown where these two groups are cis to each other. There can be one more possibility, right? In that particular possibility, if you want to draw this as cis, like these groups as cis to each other, what I can do is I can just place this methyl group to this particular position. Okay, so what I will do is I will just draw it like this. So I have manganese and I have to draw the cis product. So it's 13CO. I'm just putting it over here. This is CO, this is CO, and this is again CO, and here I have methyl group, and here I have CO. Alright, so if you look upon this now, so you can see that these two molecules are of two types. Okay, there are two ways in which you can form this. So there are two possibilities in which you can form the cis product. Okay, so cis product can be formed in two ways. One of the way is that either this or like, see, basically what is happening, that either this carbonyl can be removed from this from its place, or any of the other carbonyl, so like either this is trans to that, right? So it is not going to replace that, but yeah, either this carbonyl or this carbonyl, any of these can be removed from its place, and this methyl is going to go and bind to that place. If it goes and, okay, see, so there are three possibilities basically. Adjacent to this particular group, there are three carbonyl groups: one carbonyl group 1, carbonyl group 2, and carbonyl group 3. So if these three carbonyl groups are eliminated as a decarbonylation product, so in that particular case you will have a vacant site, and this methyl will come and bind over there. Okay, so if it goes to position 1, okay, if it goes to position 1, so this is what will be formed. Okay, so again it's a cis product, right? It's a cis product which will be formed because this and this are cis to each other. If it goes to position 2, okay, if the position 2 one is going to eliminate, in that particular case you are going to form a, again you are going to form a, like, yeah, so in that particular place this methyl group will go to the trans position of it. Okay, so in that case you will be forming the trans product. So forming the trans product, there is just one possibility, and the rest, and the next what can happen, that position 3 carbonyl can get eliminated from its place. If the position 3 carbonyl gets eliminated from its place, it is going to come and bind to this position, and when it does that, again a cis product will be formed, because your methyl will be over here and this will be CH3CO will be at its place, so both of them will be cis to each other. Okay, so again cis will be formed. So cis, formation of cis product is twice more probable than the formation of trans. We are not looking upon this particular carbonyl because this is trans to this, so we are not looking upon the decarbonylation, because then the methyl group cannot migrate to this position. Okay, methyl can only migrate to the cis position of that. If it migrates to this cis position, obviously X is going to get formed. So if there is just one possibility of formation of X, there are two possibilities of formation of cis product, and there is one possibility of formation of trans product. So if you talk about from the point of view of X, Y, and Z, so there is one possibility of X, there are two possibilities of Y, and there is one possibility of Z. So the molar ratio of the product will be 1 is to 2 is to 1. So like that you have to answer, and the correct answer comes out to be your option number B. Alright, okay, let's get to the next question. Alright, so in question number 19 over here, so the correct answer for the previous one was B. For question number 9 over here, it says the reaction of trans, this is the molecule. Let's try to draw this over here. So you have iridium, you have chlorine, you have CO. So these has to be trans to each other, right? So that should be the product. So yeah, so you have CO, and you have PPH3, and you have PPH3. That's the reactant. And in the product you can see, in the product I'll just draw it over here. So you have iridium, you have you have CO, you have chlorine, you have PPH3, you have PPH3, and you have you are bringing more chlorides to that, right? So what is going to happen to the frequency, the carbonyl frequency? So what you are adding basically is you are adding a sigma donor ligands, right? These are your sigma donor ligands, right? So two sigma donor ligands you are adding to this particular, in this particular case. So what is going to happen to the frequency of your carbonyl compound? So if you add your if you add sigma donor ligands to the metal center, so obviously your synergistic effect is going to decrease, and as the synergistic effect, like metal to ligand back bonding is going to decrease, right? And if the metal so if the metal to ligand back bonding is going to decrease, in that particular case your carbonyl frequency is going to increase, right? So the correct answer is going to be option number A, where your carbonyl frequency of the product is going to increase than the reactant. All right, and there is one more thing that over here, yeah, so that's the only factor which will work over here. Next, let's talk about question number 10 over here. It says that which of the following compounds will show highest CO stretching frequency in the higher spectrum? So you have 1, 2, 3, 4 complexes. Now you can easily tell based upon the oxidation state. So here iron is in 0 oxidation state. Here iron is in +2 oxidation state, because 2 bromine are bromine are here. PPH3 being a neutral ligand, it is also going to give you 0 oxidation state. Here it is in -2 oxidation state. So as the as metal becomes more electron, this should be carbonyl. Okay, this should be CO. So as the metal becomes more and more electron rich, if there is more electron on the metal, it is going to give electron to the anti-bonding orbital of CO, like carbonyl ligand. It is going to decrease the carbonyl frequency, right? Because the bond order decreases, the bond strength decreases, so carbonyl frequency also decreases. So metal being electron rich will show lowest amount of your it is going to show you the lowest amount of your carbonyl frequency. So if you talk about this, so this one FeCO4Br2 is in +2 oxidation state. So this is going to give you the highest carbonyl frequency, because here the synergistic effect or the back bonding, metal to carbonyl back bonding, is least in this particular case, right? Alright, let's take the next question. It says that compound A having composition FeC9H8O3 shows one signal at 2.5 ppm and another around 5 ppm in its proton NMR spectrum. The IR spectrum of the compound shows two bands around this value and the compound shows 18 electron rule. The following statement A of are correct. Okay, so let's try to draw first of all. So it's a, see, whenever in a organometallic compound, whenever you get NMR, proton NMR around 5 ppm, the most probability is that you will be having cyclopentadienyl ligand. Okay, so here let's say we have cyclopentadienyl ligand, so C5H5 has been already utilized. Now apart from that, how many you have now? Three oxygens, and if you have excess number of carbon, that means you will be having carbonyls also. Okay, so I have, let's say, carbonyls as well. And next, okay, so I have carbonyl as well, and I have like methyl group as well. So because if you calculate your hydrogens, 5 hydrogens are utilized, your carbons 5, 6, 7 and 8 are utilized, so 1 carbon and 3 hydrogens are left out. So let me just draw it like this. So is it a 18 electron species? Let's find it out. So iron is going to give you 8 electrons, each CO is going to give you 2, so 6 electrons from here, 5 from here and 1 from here. So if you calculate it, it becomes 20 electron species. So it's not correct, right? This is certainly 8 plus 6 is 14 and plus 1 is 15 plus 5 is 20. So it's not correct, right? The structure is not correct. So let's erase it a little bit. That means whatever we have drawn is not correct. So what other possibility we can have? The other possibility is that we can have this, that is C double bond O CH3. Now let's check whether it is 18 electron species or not. So, and one more thing, it shows two bands around this region, right? So two bands means generally you will be having two directly carbonyl, like direct CO attached to the metal. So now if you see, it has 8 electron from iron, 5 from cyclopentadienyl, 2 plus 2, 4 electrons from this and 1 from this. If you add them up, so now you have 18 electrons, right? So this is the correct structure. So yeah, this particular signal for 2.5 ppm is because of the presence of this methyl group. This is going to give you 5.0 ppm. Okay, so this is giving you over there. So the answer, it says that it has eta 5 CP group. That's correct. It has terminal CO group. That is also correct. It has CH3 ligand. So is it so? No, it does not have CH3 ligand. It has COCH3 ligand. It has FEH bond. No, that is also not true. So the correct option is A and B only. Answer number A, or option A, is the correct option for this question. Alright, so the next question, which says that the reaction of FeCO5 with OH minus leads to the complex A, which on oxidation with MnO2 gives compound B. The compound A and B respectively are. So I'll show you how the reaction is happening on the next slide. Alright, so let's try to see that how this particular reaction will actually proceed. So you have FeCO5, right? So let me just draw that FeCO5, and you are treating it with OH minus, right? So I'm treating it with, let's say, OH minus. So what I'm going to get is Fe, I'll be having CO, and let's say I'll be having COH. Okay, so OH has binded to the carbon because that is going to be the nucleophilic center over here, and rest of the CO are as it is. So in the next step, what is going to happen that and now since OH minus has added to the iron, so the negative charge will go on the iron itself. In the next step, what is going to happen, that carbon dioxide being a stable molecule or being a stable species, it will get eliminated, and you will form a product as this. So Fe, you will have CO, so you have CO4, and metal hydrogen bond will be formed with a negative charge on the metal. So that means first product which will be formed will be FeH FeCO4 minus. Okay, so this is going to be your compound number A. Now you are going to treat this molecule with your oxidizing agent with your MnO2. Okay, so if you treat it with MnO2 basically, so what is going to happen? Now with each iron there are 1, 2, 3, 4 carbonyl. Remember, metal carbonyl bonds are very strong, so you cannot oxidize it straight away and you can form metal oxygen bonds like that, because the probable answer now you can see is either option A or D. Option B and C you can just cancel out. So in the next step you cannot simply like do the reaction and break all the bonds. So what is going to happen is, now the other iron at like the similar kind of 3 moles of this basically is going to react with each other, and it is going to form Fe3, okay, Fe3 and CO12, because each of them is having 4 CO groups, so it will remain as it is. So the structure will be something like this. Okay, so 4 CO groups attached to that. So the final product will be Fe3CO12. So correct answer comes out to be option number A. So that is how this reaction is actually happening. And if you look upon the oxidation state of iron, so it became +2 over here. So from -1 it became +2. Okay, so like that the oxidation has happened in this particular step. Alright, so that's how this particular reaction is happening, and that's how the final product you have. Let's take the last question now. Okay, so if you look upon the last question over here for this video, it says that for the molecule given below, this is the molecule. And first of all, let me tell you that this question was asked in CSIR NET December 2012 exam. It says consider the following statement at the room temperature. Now we are doing at the room temperature, so you should be aware about one thing, that the fluxional behavior, fluxionality is going to happen. Okay, so that is going to happen over here. It says that proton NMR has singlets over 5.48 and 3.18. Is it true? So yes, that is going to be true, because you will get a singlet because of these 5 protons. Okay, these 5 protons are going to give you a singlet, and these two, like the methyl groups, are going to give you singlet. So yeah, you are going to get 2 singlets over here. Okay, so that is true. The second one says proton NMR has multiplet at this. No, you cannot get multiplet, because you are doing at room temperature, so fluxional behavior will be there, so you'll get singlet, not multiplet. Next is IR has CO stretching bonds at 1950 and 1860. That tells you that these two carbonyls are different. Okay, they are not equivalent. Obviously these are not equivalent, these are different carbonyls, because you cannot interchange them by changing these two groups, right? The groups are different, right? So this is near to this, so it will have different carbonyl frequency. This one will have different carbonyl frequency. So the IR frequency for both of these carbonyl groups is going to be different, right? So the IR has CO stretching band at 1950 and 1860 respectively. So the correct answer will be your A and C. So A and C is the correct pair of the answer. So that's it guys, that is how we have solved all the 13 questions which were there in this particular video. We have done this test series, or this particular Monday MCQ series, on organometallic compounds, and in the this next coming Monday I'll try to post on a next upcoming topic. You guys can suggest the topic which you want in the comment section below, so that I can pick up the majority of the topic which will be suggested in the majority, and I will make the next Monday MCQ on that particular thing. So that's all from my side. Thank you so much for watching, and I'm just signing off. So thank you so much and have a great day. Bye bye. Hello everyone. I'm a verified educator at an academy, and I take online live classes for CSIR, UGC NET and GATE chemistry preparation. To access my classes on an academy, you have to take an Academy Plus subscription, and that you can take for the time you want, either for 1 month, 3 months, 6 months or 12 months. While taking subscription, you can use my referral code, that is N_Huda, to get 10% discount on the referral fee, as well as to get access to my WhatsApp group. So if you guys are interested in learning live from me, you can take an Academy Plus subscription and join my classes over there. Now let's continue with our video.